So today's notes are about exponential functions, and I need to calibrate. Okay, so today's notes are exponential and logarithmic functions, and specifically we're going to be looking at our logarithmic functions. Now, first thing you want to know is that exponential functions and logarithmic functions are inverses. So exponential and logarithmic functions are inverses. Okay, so that's the important thing to remember here. Exponents and logs are inverses. So what does it mean to be inverses? Well, it means that if you plot an exponential function and you plot the logarithmic function that is its inverse, they're going to be reflections across the line y equals x. So reflections across y equals x. So for example, let's say this is my exponential function. Your logarithmic function is going to look something like this. And here's that line y equals x. And there are reflections across it. If we were to make a table of values, the x's and y's would be flipped. The domain and the range are interchanged. Domain and range are switched. So for example, let's say we have the function, well, we'll get to this in a second, I guess, when we define what logs are. But if we say y equals 3 to the x, and we have log base 3 of x equals y, and we make a chart, x, y, and let's say we start out with x equals 0, 3 to the power of 0 is 1. We do x equals 2, 3 squared is 9, x equals 3, 3 cubed is 27. When we put these same points into here, flip-flopped, if I let x equal 1, 9, and 27, what ends up happening is that I get 0 for y, 2 for y, and then 3 for y. So the domain and the range are flip-flopped, and you'll see why that's true in a minute. But right now the important thing to know is that exponential and logarithmic functions are inverses. They reflect across the line y equals x, and the domain and range are flipped. So here's our definition. So these two equations are the same but in different forms. This is logarithmic form on the left and exponential form on the right. And you pronounce this log base b of n equals k. All right, log base b of n equals k. And this is just b to the power k equals n. But make sure you're pronouncing this left-hand side correctly. So properties of all logs. Well, log base a of 1 equals 0, always. Because if I rewrite this in exponential form, I'll have a to the power of 0 equals 1, and this is always true. So that's why this is true. Log base a of a will always equal 1. And that is because a to the power of 1 will always equal a. Okay, that's why these are true. Now, this is always true. The first and the third and the fourth one are always true because of our inverse properties. Okay? And I'm not going to get into that right now. You'll look at that in your exploration in class. But this is always true. Log base a of a to the power m always equals m. And a to the power of log base a of m always equals m. Okay, so express each exponential equation as a logarithmic equation. So what this is saying is log base 2 of y equals x. And this is saying log base a of c equals b. So this part here, this is always your base, okay, your base. This is always your base, your base. Your exponent here is always what it equals, okay? Exponent, that's what it equals. And then the part that's of, this y goes here, okay? C. I think about it as kind of a circle. So, oops. There we go. So it's kind of like y, x, 2. So log, oops, I'm sorry, I messed that up. Yeah, so it's like base 2 of y equals x. Okay, you can kind of think about it like that. All right, moving on. So this one's going to be log base 2 of 8 equals 3. Here we have log base 9 of 27 equals 3/2. And this is log base 6 of 1 equals 0. And here we have log base 3 of h equals g plus 1. Okay, now we're going to flip-flop. I give it to you in log form and you put it in exponential form. So this is 2 to the power of 5 equals 32. 7 to the power of 1/2 equals square root 7. 3 to the power of 2 equals 9. And this is hard to read for me, this symbol to the power of this little Greek guy equals p. And then j to the power of l equals k. And here we have 7 to the power of 3 equals t plus 2. All right, solving logarithmic equations. So we're going to just rewrite these. So 6 to the power of 3 equals x, okay? 6 to the power of 3 is, let me plug that in, 6 to the power of 3 is 216. So 216 equals x. Here we have 6 to the power of 2.5 equals x. Now I'm going to rewrite 2.5 as an improper fraction. So that's 6 to the power of 5 over 2 equals x. And I can't take a square root of 6, and I could put 6 to the power of 5, but I'm just going to leave it like this. Okay, next. Here we have x to the power of 6 equals 64. Now, remember that we want to have, I want to know what to the power of 6 is 64. So that's 2. Okay, 2 to the power of 6 is 64. Now let's try this one. X to the power of 0 equals 2. So what does x have to be? Well, this is no solution. Okay, anything to the power of 0 has to equal 1, so this is no solution. All right, let's try this one. So this is base 10. So I'm going to think, what does this equal, okay? Remember, when there's no base, the base is automatically 10. So log base 10 of 100 equals what? So basically I'm asking 10 to the power of what equals 100? Well, 10 squared equals 100, so this equals 2. Okay, here I have another log base 10. This is our common logarithm. So I have log base 10 of 1,000. So it's asking 10 to the power of what equals 1,000? Well, 10 to the power of 3. So this must equal 3. That's the same thing. Okay. And that's it.